Hello everyone. I'm Aman Kansal, and I'd be presenting today on behalf of the headline and sentiment generation team from IIT number 9. This is the control flow that I'll be following. So first of all, I'll take you through our system architecture, and then I'll be talking about all the details about the pre-processing and each of the subtasks. Here we have the overview of our system architecture. We have as input the articles and tweets, and then after a pre-processing step, it is fed to a classification model. The details again, which I'll be talking, which classifies the articles as either belonging to tech category or non-tech category. So if the documents are classified as to be in tech category, then we have two modules. So one is the headline generation module. So it directly takes up the article classified as tech and it spits out a headline for that. An important thing to note is that our headline generation module is not at all conditioned or dependent upon the brand identification module or the sentiment classification module. Brand identification module again in turn takes the article and tweet from the those classes tech, and it feeds them to the sentiment classification module as pairs of the brand that it identified and the sentence in which that brand occurred. So the rationale behind that I'll be explaining in that section. And finally, we have the brands for each of the sentiments and brands for the articles as well as the tweets. So I'd be starting with the pre-processing step. So our pre-processing was directly inspired from the kind of data that we had. So we had online sources, that is the tweets and articles online. So we removed things like @, hashtags, and also punctuation marks, of course. And also we removed the phone numbers and the URLs that were there. Those were not useful for classification. And finally, we lemmatized the text only for those approaches where we needed to use the deep learning techniques down the line. So starting with the subtask 1 of domain classification, that is classifying whether or not the article is tech or non-tech. So here what we observed was that a bag of words approach was not only more efficient and scalable, but also gave us better accuracies and numbers as compared to a proper deep learning approach. So we had a bag of words like the company name, Samsung, MediaTek, BlackBerry, and also some generic names like smartphone, camera, earphones, things like that. And what we used was not an exact string match, but a fuzzy, or you can say an approximate string match based on Levenshtein distance, so as to factor in any spelling mistakes that were there. For example, if since these are online sources, it's very likely that the person typing them might make a spelling error, because it's people usually type on phone, so that's very common. So to factor in those things, we use an approximate string match with a high threshold, though, so as to not have many false positives or false negatives, but in fact do the accurate job of classification. So this is the approach that we followed for task 1. Now, the bag of words that we had were classified into 4 categories. We had generic words, we have brand names, we had specifications. For example, if something like gigabyte or RAM is occurring inside the text, then certainly that's related to a tech category. And finally, we had accessories like earphone and headphone. Now moving on to the second task, where we had to classify, where we had to identify the brand from the text given and also classify the sentiment. So here again, we refrained from using a deep learning model. The reason, the following were the 3 main reasons. First of all, the data had a lot of cross-linguality and transliteration. So if we used any model that was pre-trained on such a task, that always has a suboptimal performance. Those type of models are not studied as well in the literature. So we did not want to bottleneck the performances of a model at such an early stage. Also, the articles at least were very large. And in a resource-constrained environment, it doesn't make sense to have so much high runtime and memory usage if we use a deep learning approach. So if we were getting better numbers, better metrics with a non-deep learning approach, then we followed that. And finally, it's important to note that the set of companies that we have to pick are finite as well as very large. So such a large but finite set is not very well leveraged by any neural end-to-end model. So these are the 3 reasons why we refrained from using a deep learning model. What we instead did was, again, a rule-based approach where we had a bag of companies which we picked up from online sources, and then we converted those companies to their Hindi counterparts. And how we did that was the Google Translate API. So what's special about this API is that it is one of the only APIs that does a very good task of converting named entities into their Hindi counterparts. So yeah, so if you want something like techno, then you want the Hindi form of techno, and not, you don't want the Hindi form of technology. So that's what Google Trans handles very well. So yeah, so using starting with the English bag of words and adding the Hindi words to that set, we again did an approximate string match. So the approximate string match here again counters if there are any spelling mistakes, even done by the Google Trans API. Then also we have some breathing space, and that's handled by the approximate string match, which again uses the Levenshtein distance internally. And once we have identified all the important companies that are there, or not important, but all the companies that are there in the text, then we feed it sentence by sentence to the classification model, to the sentiment classification model. So, for example, if we identified the brand name Apple, then we pick up the sentence Apple smartphones are expensive, and then we feed it to a classification model, a embedded classifier model, and which does the sentiment classification in a target agnostic way. So, for example, here we have the sentiment for Apple as negative. Again, we pick up another token, iPhone. The company is again Apple, so we pick again Apple, and Apple now has two negatives. So it's important to know that if a company occurs many times in a text, it's possible that various different sentiments are associated with that particular company. So in that case, we just pick the sentiment which occurs the most number of times. And here, finally, we have OnePlus, and the sentiment there is neutral. So yeah, for Apple, we output negative, and for OnePlus, it's neutral for this particular example. And now I'd be telling you about some of the intricacies of this approach that we face. So first of all, we use embed model. So embed model is a very scalable model because you can input to embed any of the 104 languages that are there, and you need not retrain the model according to the language that you're using. So even if the model is trained on English and Hindi, the embed model handles it internally to not need any retraining. So embed model is highly scalable over languages. And another important thing to note here is that we were feeding only tokenized sentences to the embed model and not the whole articles and tweets. So articles are very large. So if you feed such a large text to a deep learning model, then obviously that has a lot of latency as well as memory requirements. And what we found out was that feeding only sentences, tokenized sentences, like sentences tokenized from the whole articles, was not only better in terms of latency and memory, but it was also giving us better accuracies. Moreover, if you follow such a tokenized approach, then you can use the combined data from article as well as tweets to train a single model. So for a single model, you have more amount of data that you can use to train that model. And moreover, if you anyway use a different models for articles and tweets, then that's an added memory usage. So yeah, so we tried to be resource efficient at the same time improving our accuracies in this approach. Also, we pre-trained, apart from the dataset that was given to us by Bridgei2i, we also pre-trained our model on Semival and also its translated counterpart. Its counterpart translated to Hindi. So yeah, so just to make the model more robust. Yeah, so concluding this, and then I'll move to the third subtask of headline generation. So for the task of headline generation, I added we added another pre-processing step where we converted all the text that we had from articles to English. We used the Translate API for that. So the good thing about Translate API is that you need not specify the input language, the source language from which you want the translation. So that means the model that we have rolled out currently is already scalable across all the languages that are there. And in the backend, the Translate API, you have a multiplex of various translation servers, which are from like Google, Microsoft, Baidu, and all those tech giants. So the translations are also pretty accurate. So once you have the translated articles, then before telling you about the approach, it's important to see the data distribution here. So it's in terms of the number of words that are there in the article and the number of words that are there in the headline. So as you can see, the headline, we were constrained to output max 20 words, but the articles could have been of arbitrary length. So the compression ratio, first of all, was very high. Moreover, if we use any out-of-the-box summarization model, then Usually those summarization models have the pattern that the output summary or headline is always proportional in length to the articles that you have, to the input text that you have, and that distribution was not at all there. In like that distribution was not replicated in the data given to us. So it's important to fix that distribution issue before we before we train on the data given to us. And how we handled that was using the XM dataset or the extreme summarization dataset. So XM dataset has the following pattern. So for every article that you have in XM, the headline that the output it gives is the answer to the following question: what is the article about? Now, this may not be exactly the headline. It's slightly different, but in terms of data distribution, so even for a large article, the output of what is the article about will still be this. So that data distribution is replicated here, and even the data itself. For example, we in Bridgei2i article we have, let us say, article length of 603, and the headline length was of 16. So even for exam, the articles are quite large, like 431 words, and the headlines were still in range. We were constrained to 20, but still 23 is good for pre-training. So we use the models which were pre-trained on exam and not directly the summarization models that we had. And another insight that we had in this approach was that we did not throw away those articles that were classified as non-mobile tech in the first step. Why we did that? Because they were not completely useless. So though they don't teach you to output words of that particular domain, they still teach you how to adapt to the task, how to achieve that large compression ratio, and how to achieve that data distribution. So we found that using even non-mobile tech articles as training in this task improved our metrics as compared to using only the tech classified articles. And obviously there are those tech classified articles as well, and that they do teach you how to output words corresponding to that particular domain. And yeah, as I said, that we get better metrics with using both these data sets and not just one of them. And finally, coming to the model that we use, so BART is a very generic and very widespread model that is used for such kind of tasks. But there's again a catch. So BART is a very complex model, and it has a humongous number of parameters. So and the data that we had for training in our last task, that is the data from Bridgei2i, it's quite small. So if we use BART to train on such a data set, that will mean that the model overlearns, like it crams up everything, it crams up the data set, which we don't want. We wanted to learn the pattern. So for that, we used a lighter version of BART, a distilled version of BART, which is called the distilled BART. So, and using distilled BART, we not only observed like the parameters were low, and hence the training time as well as the inference time and the space required was low, but also the Roche scores were better for distilled BART as compared to BART. So, yeah, execution was verified with the experiments. That was the approaches that we followed for all of the tasks. Now, I'd like to conclude with saying that through all the approaches, we tried to pick up the simplest approach that will give us the best numbers, and we try to innovate in that way. Also, all the models that we had are totally scalable across languages. So, regardless of the input language, our models can work. And finally, we always try to minimize the resource through all our subtasks while not compromising in terms of accuracy and metrics. So for task 1 and part 1 of task 2, we did not use any deep learning models at all. So that's already very efficient and memory, and low on memory. But even where we use Ambert, there also we were not feeding the whole article. We were just feeding it sentences, which saves a lot of resources. And finally, instead of blindly using a model like BART, we tried to find us a model which was of lower size, lesser size, and lesser complexity, which is the distilled BART. And we found that it even did better. So we were quite happy that we had a win-win situation over resources as well as metrics, and that's for the pitch. And I would really like to thank you on behalf of the whole team to give us the opportunity to work on this problem and learn for it. And the whole team is now open for questions. Thank you so much.
Thank you, Aman. So now the Q&A round will begin. Judges, you can ask question.
I can go first. Thank you, Aman. Just checking, can you hear me?
Yes, I can hear you. Thank you.
Audible?
Yes. Yes, ma'am.
Perfect. So, you basically using something like a context detection. So, if there is a brand name that is given and there is some generic word related to iPhone, you try in the context saying that this phone is now talking about the brand sentence. So my question to you is that brand retention or the context retention, is it unidirectional, bidirectional, and what will happen to a scenario where there is a phone word written and it is followed by two different brand names? So that word for a phone will be given to which brand? It's the first, let's say Apple brand, and the next sentence, let's say Sony brand. Do you understand my question?
Ma'am, can you please repeat some part of can you please repeat the question? I think there was some network issue in between, so it would be helpful.
Sure. Can you hear me all right now?
Yes, ma'am.
Okay, so let me try again. So in your sentence tokenization, I think you are doing a context retention, right? The context retention is what I mean is there is a first sentence which mentions brand name Apple. Then the second sentence, which basically says something about only phone. Then you're saying that since this sentence is followed by Apple, this phone word or whatever sentence is, it's talking about that Apple brand itself, right? My question to you is, your context retention is unidirectional, bidirectional, and how do you manage a scenario where the word phone is present with a Apple sentence and with a Sony sentence? So where do you assign the word phone to?
Okay, I understood the question. So let me answer that. So the approach that we are following here is that we are keeping a context of sentences around. So let us say there is a sentence which mentions Apple, and followed by there's a sentence which mentions phone, and following that there's a sentence that mentions there is a sentence that mentions maybe Nokia, right? And now the phone sentence might be associated with both either Apple or Nokia. So we keep that particular context alive. We don't miss it out, and we allow the since we are using a BERT model. So BERT model is the context in MBERT it is, but still the word. So MBERT model handles context internally. So it's a bidirectional context. It's a self-attention approach. So the context is obviously bidirectional, and it's already known that the BERT models can handle such tasks of entity resolution or entity linking inside the text implicitly. So ideally, there is no need for us to handle that directly, and yeah, we just left that to the deep learning model that was there and enhanced.
Sure. So there was no other extra step taken by you. It just based on your understanding, MBERT would have handled this. Am I right?
MBERT would have handled this, and another insight here is that I won't say usually, like from our inspection in all of the cases, the any sentence that talks about a tech always talks about the company that precedes that. So an approach where we also tried that approach, and so that's why we minimize the context. So we started with a large context initially, but we minimized the context to 2 because that was enough. A sentence following that always talks about the company that was mentioned just before it. So a context of size 2, like that is just the sentence after, is also good enough. Thank you so much.
Thank you so much.
Go ahead, Jayadri.
Okay, sure. Thanks, Jaskaran. So I think, Aman, I think one thing you mentioned, I not sure if I picked it up rightly, is that your approach of handling language scalability was to translate everything first and then apply your models on the translated data. Did I get that part right?
That's partially correct, sir. So for in the subtask 2, we use an AMBERT model. So AMBERT model does not require any translation in itself. So AMBERT
Sure.
model can be directly it's cross-lingual in itself. So for that there was no need of translation. But for other tasks such as task 1 or even subtask 3, yes, we did translate the article, and uh, that's how the language scalability was handled. That's true.
And do you have any sense, or can you share us any observation that you have had in terms of the accuracy that you saw for English language data as opposed to Hindi language data post the translation? I mean, does it impact it in some manner that you have observed or anything like that?
Okay, I don't think that we have the metrics right now. Anyone from the team can speak of if somebody knows anything about it. But
Okay.
like the okay,
Yeah. So for task one, there wasn't really any difference because we were using both in the bag of words, both Hindi and English words are used. So there wasn't any need for a separate translation in that. But for task three, I think, yes.
right.
Yeah. So for task 3, we were translating it to English language because the headline generation has been like has been it has been worked upon mostly on English language. So there was no available models for to work upon, and not much available data to work upon other languages. So that's why we thought, and quite naturally, it was the first instinct to translate all the articles to in a single language, English, and then work upon headline generation. So the library we have used actually supports 104 languages, which is also supported by AMBER. So the model that the task 3 pipe we have given already scales up to 104 languages.
I'd just like to add something on that, sir. So, in all the in all the solutions that we had, we always had an almost equal representation in terms of training data of English as well as Hindi. So, for example, we had Semeval. We translated Semeval to Hindi also, and then we had Semeval Hindi version as well. And even whenever we had bag of words, we had all the English words as well as their Hindi counterparts. So in none of the approaches is there any weight difference in as compared to Hindi and English, and even the data that was given to us was quite balanced in terms of languages. So there's no reason to believe, for us, there is no reason to believe that there should be any difference in accuracies over Hindi or English or any other language for that matter.
Got you. Thanks for the answer. Thank you.
So just extending to what Joydeep was asked, an extension question. So basically, you handled English and Hindi, but what about English? How did you handle that? Because that's not been called out in any of your slides or presentation. How did you handle that?
So yeah, actually, 3 English or even translated Hindi words, they were also converted into English language. The library handles automatically detects the input language, even the translated Hindi words and even the English sentences, and converts them to English words. So Aman, if you can go back to slide 3, it's
Sure.
there. Yeah.
Slide 3, you say?
It's not the task 3.
Okay, task 3.
Yeah, there. So even in the English translated Hindi articles, all were converted to language, and then we were worked upon headline generation.
Yeah, and in task one, we didn't need to take care of transliteration because we only used the bag of words, and it had both in English script and in the Hindi script. So English wasn't even needed. English anyway would go with either one of them.
Okay. So one issue, like say suppose there's a tweet called I love eating apples, right? That's a tweet. An apple here is a fruit, but when you do a bag of word technique, you detect apple as a keyword, and apple has already been a brand for you, right? So your model will tend to classify that tweet as a mobile tech tweet, even though I was just talking about a fruit. how do you ensure, say, even if you use a bag of word technique, how do you ensure that such scenarios don't pop up?
That's the right question. So the thing is that like we initially started with only some very generic words like smartphones and accessory words, and only for handling some of the corner cases we added some company names, and we added very few company names. So not the set as large as we did in task 2, and this is a concern that we recognized early on, that if a company name matches a real life entity, then that would be an issue. So we just tried by adding those company names that had no real world entity relevance. For example, we don't want to add Apple, obviously, and we don't want to add, let us say, Intel, yeah, so because Intel and intellect, so these things can match. Although the threshold of the approximate string match would be high enough to prevent this, but yeah, we refrained ourselves from adding such kind of words to that. And the word set for task 1 was self-designed, and we were already getting accuracies like without even using only a very small data set and observing the words from that and picking out very generic words, very small set of words. We were already having 95% plus accuracies, and that is without any train or test overlap. Without any data leakage, we were getting those accuracies. So we added only a few generic very few specific company names, and that's it. Nothing more than that.
And adding to that, we use this bag of word method because for the given that was made available to us to analyze, we found that the way the annotations are being done, it was clear that the data generation process itself was following some kind of string matching with a bag of words. So that is why we felt that if the larger data set from which this data set has been sampled, the data generation process of the larger data set, if it reflects the same probability distribution, we can actually get that classification accuracy high if we just use a simple bag of words method. If we had found that we would need much bigger contextual information for classification, we could easily go for a complex language model. But for this particular data set, when we analyzed it, we didn't feel the need to go for it.
Got it. Yeah. I think we are done. Don't have any other questions.
Okay, so
Okay.
thank you everyone.
Thank you so much. Thank you so much,
Thank
ma'am.
you.